crazy, but how about a vector field 1, 2, 3? Guess what you notice? Are there any variables in there? Here's a three-dimensional vector field. So if there's no variables, every one of the vectors should be the same size and the same, what, direction?
Mm-hmm.
Yeah. They should all move 1, 2, 3. And it could look something like this. I made this with wind plot. But they're all, notice they're all the same length and the same direction. Same length, same direction. That's just a three-dimensional vector field. I thought I'd give you another one just to look at. What if it did have variables? So let's look at one like that. These have been scaled down, everyone, because you can see they're almost running into each other. But this is the vector field x, comma y, comma 30. So what's going on at the point like 1, 1, 1? It would move what? 1 in the x direction, 1 in the y direction, and 30 upward. But do you notice with this vector field, because the third component, the k component, doesn't have a variable, and it's 30, every one of these vectors should be pointed which way?
Oh.
You see that? Because there's no variable in the z component. And that's what you'll notice in this vector field. They do change sizes. These have been scaled though. That's why they look, it's like a unit vector field where it makes them look all the same way. But you'll notice all the vectors are pointed up. That's what's going on with that thing. Cool? Hey, awesome. Well, I will turn this off for now. Take that. Take the light. One more thing. What if I give you a function? Nothing crazy. A function of x and y. That's not a vector field, right? But this is in section 16.1. So we're in section 16.1, and I give you a function of x and y. I'll read it correctly. Okay. Here we are in vector fields. Gee, nothing crazy. How about ys? Whoops. I'm actually screwing up making a vector field. This is a function x and y. How about just something like, a scalar function? How about x times y? And here's the directions on the book. I want to tell you which problems this is like on the book. This is a problem like, number 21 out of 16.1. They go, sketch the gradient vector field of that. So vector fields, we're talking about vectors, we need a vector field. What's the gradient again? Do you remember the definition? That's the vector that's made up of what in terms of f? See, that's not a vector. Yeah. Outstanding, Andrew. We're talking about the gradient. I'm going to put del f here. Remember that was the notation for gradient? Or you can put what? G-R-A-D. Gradient, a function is vector. Del f is the gradient. It's just the vector field made up of the partial derivatives. But this is what they're talking about. They want you to sketch this. What is f(x)? What's the derivative respect, partial derivative respect to x?
Y.
What? What's the partial of that function with respect to x? I mean with respect to y.
X.
X, right? And now you can start plotting the vector. And then you move from there. So if you work those problems in the textbook, I didn't want you to get confused by problems like, this is similar to number 21, where you go, what do they mean this didn't have a vector field? They said sketch the gradient vector field. Yep, they just want you to get the partial derivatives, respect to x and y, and then you start plotting. And you know how to sketch that, right? Let's sketch one vector. How about what's going on at the point -1, 1? That's y, x, that's y. How would that move? It would move
-1.
1 in the what? Y direction, and then -1, isn't that the movement? So let me go plot that. At -1, 1, it should move right 1, and then down 1, which would look like what? Inward. And you just keep plotting away. All right. Hey, so now we're moving to line integrals. Two types of line integrals we'll be working with today. Line integrals of a scalar function and line integrals of a vector field. Well, here's the formula. Line integral of a scalar function. Can everyone see that? I'll even put it right here on the board. The line integral of a scalar field. Or scalar function. Is written as, first, they put a C here. That C represents actually the curve. So these are called line integrals. Maybe we should call them curve integrals. Most of these problems are going to have curves. All right, and they were a function of x and y, and then they put ds. Okay, what the heck does this mean? First of all, I want to talk about that ds. This ds is represented by this right here, if it's two-dimensional space. If you're talking about a curve in two-dimensional space, that C represents some curve. If it's in two-dimensional space, like a vector curve, you know, that we had before. But this is what ds is. Now, did anybody need me to derive that? I remember you asked me, like, gosh, a couple weeks ago about deriving like the length of a curve. But it's very similar. If you want me to derive that, I can do it real quickly. Anybody want to see where that comes from? You everyone okay? Everyone's okay? What do you think?
I don't know. Okay.
It'll only take a couple minutes. We can talk about like where that came from. It actually came from like if you just had a length of a curve, you start out by thinking a distance between 2 points on a curve. So what's the distance one? I'll just derive it real quick. It won't take long. What's the difference? I can think about change in x squared plus the change in y squared. Okay. But do you remember something called the mean value theorem for derivatives? And it said that dy dx equals change in y over change in x at some point c between 2 points. Because the whole idea, if we're trying to get the length of a curve, we got to break this into what? Just an infinite amount of small segments, like this, and send that limit towards infinity. Okay. Anyways, what does change in y equal to there? We can substitute. What's change in y equal to? dy dx times a change in x. So I'm going to put that in here. Look what you get. You get change in x squared plus, I'm going to put that in there, dy dx, change in x squared. So far, so good? All right, now, what can I factor out of that mess? Here, I'll erase this. Let me put that in there. Can I factor out a square root of x? And it's got to be positive, so I can factor it out of here and just put it in front of the radical. Well, what are you left with? This becomes a 1,
Plus dy.
and you got a dy dx all 1
Yeah.
squared. You go, okay, but sum a bunch of these. You're like, aha, infinite sum. We go, all right. I go 1 to n, I'll send a limit towards infinity of all these. 1 plus derivative of y with respect to x squared, and then it had a change in x, right? But this turns into the integral. And you go along the curve from a to b, 1 plus dy dx squared. And what does this become in the integral? Just a dx. Isn't that cool? So this is actually the length of a curve, or when we just came up with how you get the length of a curve. But that's if it's in terms of y's and x's. Everything we're dealing with now is parametric. So how does this get formed? So I'm going to take this one step forward. One step further, we'll talk about that right, okay, everyone? We'll take it one step further, I'll write it right up here. Get this out of the way. We'll be dealing with that in a second. So what do we have there inside that radical? 1 plus of what? dy over dx, and it's all squared. I'm going to enlarge this radical for everyone. And how about we divide dt here and a dt there? So I'll do it there and I'll do it there. And when I just multiply a 1 to this, can I do that? I can multiply 1 to it. And then, this had a dx outside, so I'll multiply that by dt over dt. And look what happens. if I take this dx dt and multiply it back into the radical. So if I multiply this back into the radical, I gotta think of this as square root of dy dx squared, right? When I put that back in, look what happens. This goes back in here. Dy dx
Square.
squared. When I put it here, it's gonna cancel with the what?
dx dt.
I mean, this is I apologize. When I put a dx dt and I put it in here, it would be a dx dt squared. When I multiply here inside, it's going to cancel that out. And then you'll just be left with that. So all I did is when I put this back in the radical and distributed, look what happened. And we just formed what? What we call this ds. So thanks for being patient on that. I just wanted to see where that comes from. So that ds, you might be in section 16.3 and go, what's ds again? It's the square root of dx over dt plus dy over dt. There's another way we can write that. We can write this as ds just equal to the magnitude of some r prime of t dt. You all agree? Is that another way we can write it? So, the formula's going to what's the line integral of a scalar function? I'll put it back up. It becomes the line integral of a scalar function will be take the function of x and y and multiply that ds. Well, let me do that again. Because we're going to make all this parametric. C is the curve. We'll write the function of x in terms of t, make sure y is in terms of t, everything in terms of the parameter t. So what does this turn into? Well, I'll use this. And we need to write that, but I'll write this one. Just the magnitude of r prime of some t. Okay, so we got our formula, but still, what does this mean? Can we visualize this? So I'm going to go to that. I want you to, can we see that? What are we really finding? It'd be silly if you and I just start working problems like, okay, what does this really mean? I'll make sure that's where we'll use that. Let's see. Use this one right here. Ooh, what does this really mean? This line integral of a scalar function.
I jumped off my bed.
Oh good, it's coming through. Here's what we mean. You'll see in this picture, everyone, the line integral over the scalar field can be thought as the area under the curve C along a surface Z as a function of x and y. And I'll wait till this fades in a little bit with the colors. I'll show you where this applet starts. This is a pretty cool applet. Like, yeah, we got the wrong. So everyone, here's some surface, some function of x and y. It's the contour map. We're like, okay, can we see it better? And I'll tilt it back down. There's some path, some curve from A to B. But tilt this back down, you can actually see the hills in terms of that contour map. Oh, okay, there's like that, some function of x and y, three-dimensional. But you can think of this line integral of a scalar field can be thought as the area under that curve along some surface. And we know when you do an integral, underneath here would be represented as a negative value. Above here would be represented as a what? It's a positive value. So you can get line integrals that are negative. You can get line integrals that are 0 because of this. But you can always think like, what am I really finding? There's some path C, all right, over some, a surface Z, some function of x and y, and we can think is the area under the curve C along that surface. Along that surface. That's what we're finding. All right. So we'll come back to that. And then eventually we're going to do a line integral of a vector field. I'll pull this thing right back up and we'll do another image too. But let's work a couple of these. So I'll turn this off. Let's work a couple of these line integrals of scalar field functions. So here's the first one. Let's find, and if you don't want to copy it down, the problem I'm using is from the 16.1 to 16.2 practice problems. Okay?
Can I ask you a question?
And I want to use, we'll start with number 5.
Can I ask you a question? How do you calculate the magnitude of the R over here with the parameter, do you do that like x squared plus y squared the same way?
That's exactly it.
Oh,
That's exactly it.
okay.
And that's what you do to get that magnitude of that.
Okay.
And so in this, very good. And that's what I'm saying here is like some R what? Some R represented some
X cosine theta.
X and Y.
Uh-huh.
Exactly. And so we're saying what? R, some function X and Y. It's got some X of t here and it's got some Y of t here. And then we're taking the magnitude of just the
X and y.
derivative of X, derivative of Y, and they get squared. Excellent. All right, Owen, here's what they said. You gotta evaluate this. Evaluate. I'm using number 5. C, Y, ds. So the minute you see this, and we have not seen this notation before until this section. We have never seen a single integral written with this little c there off the corner. So that means line integral. That's the notation for line integral. You might think it'd be better to call them curve integrals. Because did you just see a line or a curve in that apple?
Curve,
It was a curve. So you might go, why don't they just call them curve integrals? Because they're rarely lines, right? But they call them line integrals. So they write this, and what else did they write for this problem? They said, they got to give us the curve. Here's C. Here's your curve. They said the curve is, they give you the equation, x is t squared. And what was the y component? Y is 8t. Does anyone see this as parametric?
Uh-huh.
Yeah, the parametric equations. And going from 0 to 3. So we just got to find what? Function composed of RT times this will just be the magnitude of the derivative. Which will be that. Alright, so I'll put this here. And you'll see that's written like that on this sheet too. Oh, good. Zero to 3.